Operational Robots by Dr. Rajesh Kannan Megalingam. Dr. Rajesh Kannan Megalingam is an electronics engineer leading research on humanitarian technologies with special emphasis on robotics at HUT Labs, Amrita Vishwa Vidyapeetham University, and assistant professor in the Department of ECE. He completed his undergraduate in engineering from College of Engineering, Anna University, Chennai in 1997 and Masters and PhD at Amrita Vishwa Vidyapeetham in 2010 and 2015 respectively. His research area includes embedded systems, robotics, semiconductors, and healthcare. His research focuses on autonomous robots, vertical climbing robots, robots for rehabilitation, and robots and VLSI, etc. He has 7.5 years of work experience and more than 11 years of research experience. He has worked as VLSI design and verification engineer at various companies like ST Microelectronics, in Silicon Incorporation, etc., in Bay Area, California, USA, for 6 years before joining Amrita in 2004. Since then, he has published more than 80 research papers at various international conferences, journals, and book chapters. He has 4 patents to his credit. He is currently guiding 2 PhD students and several teams of bachelor's and master's students as research assistants at HUT Labs. He is also actively engaged in teaching and guiding several teams of undergraduate students in research and competitions. He is the IEEE Student Branch Counselor, which has won several national and international recognitions, awards, project fundings, etc., under his leadership. He has won several awards, including the Outstanding Branch Counselor and Advisor Award from IEEE New Jersey, USA, Outstanding Branch Counselor Award from IEEE Kerala Section, and the Award of Excellence from Amrita Vishwa Vidyapeetham, the highest award by the university. He is also the recipient of 2020 IEEE Undergraduate Teaching Award for his exemplary role in encouraging undergraduate engineering students to take up research for developing innovative solutions for the society. Recently, he received the award virtually from Dr. Toshio Fukuda during the flagship conference of IEEE Education Society Frontiers in Education, FIE 2020. Now, I hand over the session to Dr. Rajesh Kannan.
Thank you very much for the introduction. And I think that's a little bit outdated one because some of the numbers are almost double now. Anyhow, a very good afternoon to everybody. And I take this opportunity to thank Professor Deepa and TalkEdge Institute for inviting me to this part of the short-term program. So let me share my screen and we'll start. Can you see my screen?
Yes, sir.
Yes.
Yeah. So the topic is going to be on sensors and actuators, particularly navigational robots. So these sensors and actuators play a very critical role in building a successful robot. In fact, anything like artificial intelligence or machine learning, you cannot think without sensors and actuators. So these being a crucial part of the robots, we are going to discuss about some of these sensors and also actuators. And how I designed this lecture is that there are going to be some video presentations in between about some of the projects that we have completed or we are currently doing at the Humanitarian Technology Labs at Amrita. So by that way, you would be able to relate some of these sensors to some of the real-time projects that are going on at Hut Labs. So you can see the numbers and all changed here. So the lab was established in 2012, and one of the important thing that the lab undertakes is that the undergraduate research. It encourages so much, and the research is in the direction of humanitarian technology projects, right? And because of that I received the 2020 IEEE Undergraduate Teaching Award. That is one of the strong reasons. And you can see some of the projects listed here. These undergraduate students, along with several others, have completed or currently going on. The first one is Amaran, an unmanned robotic coconut tree climber and harvester. Mudra, a hand gesture-based wheelchair. Selfie, a self-driving powered wheelchair. Paripreksha, search and rescue robo. Paricharya, a service robo. Suraksha, IoT-based crop protection system. And a robo army itself for dealing with the COVID situation. Robos for food drug delivery, robo for UV sanitization, robo for transporting patients without contaminating the environment, and a robo for public awareness. So till date, there are more than 600 undergraduate researchers who benefited from several projects at Art Labs, and currently there are 52 undergraduate researchers. And you can see that our research publications is 160, right? More than 160 now, not 80. Right? That was, I think that was taken from the website, which was updated last in 2015. So several journals and conferences and book chapters published. And it's not 4 patents, we have 11 patents so far. Like one is already approved, 10 is pending. And the approved patent is for the robotic coconut tree climber. It was a US patent, which was approved in August, I think, this year. And also 2 startups, right? That is also another thing from some of the research projects. We could successfully come up with 2 startups. Okay, anyhow, now being this being the introduction, we'll dive into the topic. So I have divided into 2 parts. The part 1 is the sensors, and part 2 is going to be the actuators. As I mentioned earlier, sensor plays a key role, right? And without sensors, you cannot imagine any software at all, right? Well, a successful robo depends on the several departments coming together, right? Even though some department can claim that robotics is part of theirs, in reality it is not true. You need a very good mechanical structure which passes dynamic and kinematic equations so that the robo is stable. You need a very, very advanced algorithms, right? A very good software that should be part of the robo. You also need the sensors, the actuators, and other stuff. The electronics part, which is heart of the system, a control system, not in the sense of the course control system. I meant about the controllers, the microprocessor, microcontroller you need in order to execute this software and control the actuators. So you can see that without all the departments coming together, you cannot build a successful robot. All right. So this is how I have arranged the presentation. The case study is not going to be at the end. It's going to be in between some of the projects so that it's not boring, right? It's usually after lunch. Everybody might have a good lunch, right? You know how difficult for us to have a class in the afternoon, right? Now we are all taking it online. We don't know what is happening on the other side, but at least when we were conducting the classes, right, physically in a classroom, it would be very, very difficult to keep the students awake. And now we undergo the same situation. So I'm introducing a little bit videos in between to keep the lecture alive. Right. So before census, we need to know this term transducers. We all know, everybody who teaches electrical or electronics, right? Transducers converts one form of energy into another. If you take microphone, it is sound into electrical energy. If you take solar cells, it's light energy into a thermal energy, right? Or into electrical energy. And a light bulb, if you take, that's light bulb is also a transducer because it converts the electrical energy into optical energy. And an electric motor converts the electrical energy into a mechanical energy, a rotational force or a motion. Right, a note is given here. Actuator is a device that actuates. Anyhow, actuator we are going to discuss more in the part 2. Right, but one thing to mention is an actuator also uses energy to provide the motion. So in one sense, you can also call a actuator as a transducer itself. So in the previous example, you could see that the motor, the electric motor, you can call it as a transducer in that sense. Right. So there are so many categories of transducers. Electromechanical, right? Some of the important in electromechanical, you day-to-day life is battery, right, which converts chemical energy into the electrical energy, right? Then electroacoustic, right, loudspeaker or microphone we deal in day-to-day life, particularly during online classes. Then electromagnetic transducers, obviously generator, which is a common example. Then electrostatic, right? We might not have dealt with that. This is not commonly used or commonly we see everywhere. Then electromechanical, obviously motors are supposed to be electromechanical. Generators also. Some of you might have used strain gauges, right, to measure the force or the torque. Then comes the photoelectric transducers, right? You would have dealt with the, obviously a light bulb is a photoelectric transducer. In labs or for projects, you might have used photodiodes. There is also thermoelectric, right? Temperature measurement LM35 is a thermoelectric temperature to electric pulses. And there are other types like quartz crystal. I don't know how many of you know that. So it's kind of a mechanical stress. You can see there is a crystal, and depending on the stress, right, it can generate a pulse. So these are all so many types of transducers, right? But it's always kind of interchangeable, right? Most of you use the word sensor, even though some of that might be a transducer. But that is still okay as long as you know that the sensors converts the input in any form into electrical signal. So in that sense, all the sensors are going to be called transducers. According to the ANSI, that is American National Standard Institute, the definition for a sensor is given as a device that produces an output in response to a specific measurement. The input is kind of a measurement. Right, so the setup is shown here. There is an excitation here, that is the input, and then the external sources, the power source, and you get some output, right, in the form of analog signals. So that means you can see that this is a random signal, right? So as such, the information is there in the signal, but it's not ready to be processed. That means you have to apply analog to digital, and then somebody has to work on the digital data and then get a meaningful or interpret a meaningful information from this analog signal. So these sensors acquire physical parameters and convert it into a signal that is suitable for processing. Right? And you can see the sensors are used in all aspects of life. Whether you know it or not, you are already using too many sensors daily, almost maybe throughout the day. If you have a mobile phone, that means you are already dealing with a sensor system itself, which is a complicated combination of several sensors. Right, so this is a typical difference shown here. When you classify something as a sensor, when you classify something as a transducer, you can say that transducer, you already know the definition. In general, it converts one form of energy into another form, but they do not quantify the conversions. That means the output is not meaningful for us to interpret. Right. So now if you're in your room, if your light is switched on, you get a brightness, right? But that is a transducer, right? But how much brightness, how much lumens, right? You don't know. So once you go into that aspect of quantifying the amount of output through some processing, then the word sensor is more suitable. Right, so we already have 5 senses: eyes, touch, your hands, skin, your nose for smell, then the tongue for taste, and the ears for hearing capability. Right, so the brain is the heart here, it processes whatever the input in the form of the sense organs, and then we get a meaningful output. Right, so any of these sensors receive signals and messages the brain, which outputs a response. Right, so when you feel something hot, when you taste something sweet, it is always the brain that is giving out this meaningful information, not your skin or your tongue. Right, so now we are going to go into the types of sensors. All right, so if you are already into building some robotic projects, you might have come across some of these sensors. All right, thermal sensor, obviously some kind of temperature sensor you might have dealt with. Mechanical sensor is very important nowadays. So many things happen, right, where you need to measure the pressure or the acceleration, right, and the liquid flow, particularly when you go to a Pizza Hut or somewhere where you have a Coke dispensing machine or a soft drink dispensing machine. You need this liquid flow sensor to measure how much liquid flows into the glass and stop if a particular amount has already been dispensed. Right, electrical sensors, right, most of this we would have used in the labs, particularly electrical. Right, chemical sensor, CO2, some of you might have used in your project. Right, CO2 sensors, they are useful for detecting the presence of the human being, right? So that can be used in disaster management to identify victims. Then optical sensors, these are all common sensors which the student build the projects like LDR and all. IR, those things are all commonly used in many of the student projects. Then acoustic, right? wave velocity in the air or something like that. So here is a table which gives the stimulus or the input to these sensors and what is the quantity measured. Right. So on the left hand side you see the stimulus, what kind of input to these sensors and what all things that we can measure. Right. So before we continue, right. So one video demo is there. Right. So this is a project, as I mentioned, um, which won several recognition. It also won the IEEE Foundation funding of around $7,800. I think this was the first project that was funded by IEEE um, in our campus. That's long back, maybe 8 years before. And it also won the IEEE, I don't remember, a few other awards it won. So this is about recognizing the hand gesture, right, and then control the wheelchair. The goal is to help with the quadriplegic patients or the elders who don't have much strength in their arms to hold the joystick, right? You would have seen the powered wheelchairs. Commonly, the control interface is joystick, but you need to hold it and operate, keep operating it, right, continuously. For that, you need to exert some pressure, and your hands should be at least healthy to a moderate level. But from the study we did, right, we found that all the elders, right, they are not comfortable with this joystick, and then quadriplegics, we don't need to think about their hand strength at all because they totally lack strength in their hands. They are paralyzed, right? But through some therapy, right, this is what we found out from Amrita Institute of Medical Sciences. We did this project in collaboration with the physiotherapy department, right? So after some physiotherapy, these patients can regain some strength, right, in their hands. At least they can move their hands. So for such kind of patients also, this kind of wheelchair would be very useful, right? So it captures a very tiny movements of the hand, the control unit that we design. In fact, that is the first patent we applied because the control unit is based on a simple IR sensor array to detect the movement of the hand. Till then, cameras were used to capture the hand movement and do some video processing and find the hand gesture. But obviously, camera costly solution and also fitting in a wheelchair with the user comfortability and other things, it was not as we expected. So that is why we came up with this platform. I'll just play the video. Let me know if you are able to hear the sound. Right? Often it happens that there is some thing going on with the Google Meet. Right? Can you hear?
Yes.
Can you hear the
Now,
audio?
now it's not audible, sir.
Yeah, I stopped it. Okay, I'll start
Okay.
again. Yeah.
Sir, not audible, na.
Not audible?
Not audible, sir.
Okay. What about now?
No, sir.
Okay. I think I need to go back to the. So there is a. I need to share the audio of this Google Meet, I think. Okay, what I'll just quit the Google Meet for a moment, right, and then I'll log in. Excuse me. Okay, can you hear me?
Yes, sir.
Yeah, so I'm going to try again playing the video.
Okay, sir.
Can you see my share the screen?
Yeah.
Can you hear the audio?
No, sir.
Okay, one second. Okay, there should be a way to share the computer audio. I used to do that. Can anyone know how to do that? Okay, let me check if I can get some help from one of the staff at the lab. Okay, it seems that with the Google Meet, there is no option to share the system audio. Right, so the video, anyhow, I think I need to explain what is going on in the video. So um, let us continue with the presentation.
Sir, you can actually put up a speaker to the computer and then video it, and you can put up the meeting in your phone, and then the audio can be heard via your talking, how you talk.
Oh, okay, so that is the way to. Okay,
There is no
so
other option.
okay, I don't know why it is like that because normally I conduct meetings via Zoom or WebEx. That option is there to share the system audio. But anyhow, let me share. You are able to see my share the screen, right? Yes.
Ah, yes, yes, we can see the shared screen, but now you are not sharing, I guess.
Okay. Now, okay. Let me check again what happened. Okay. Can you see my share screen?
Yeah, it's very
Yes,
clear.
sir.
Okay, so then I'm going to give you a live commentary on the video, right? So let us see. Um, you are sure you are not able to hear the video, audio?
No, no, sir.
Okay. Um, yeah, so let me.
Sir, can you increase the inbuilt volume of the lab? Maybe that's why. If
Okay, maybe, yeah, I can give the.
can you
Uh,
increase it?
yeah, I will increase it. Okay. Can you hear now?
No, sir.
Okay.
Volume.
Now?
No, sir.
Okay, fine. Anyhow, we don't need to waste time, right? So as I mentioned, I'll give the live commentary.
Okay, sir.
All right, so you can see that people often use in India mechanical wheelchairs because for some, even the electrical wheelchairs are not affordable, right? So most of the time, there is also a social issue with dealing with people using the wheelchairs. Most of the wheelchair users are ignored, right, even by their family members. So that is the situation in India. And here you can see the joystick control unit is the default control unit, right, and used in the wheelchairs. So here this is the gesture pad. We call it as G pad, which is made with the IR sensor array, and the user can move the arm over the IR pad or the G pad. So, so you can see this is group of students, BTech students working on that. I will skip this part, right? So you can just move the hand over this G pad, right, and then left or right or straight or stop, all right, so that accordingly the wheelchair can move forward or reverse or right or left. We also developed a mobile-based app, an Android app. You can see a tablet is used with the app with the arrow marks. You can just touch the arrow marks, right? Whether you want to go forward or reverse or left or right. And the advantage is that even the nurse or the caretaker can control the wheelchair. If the patient is really, really sick, even the hand gesture is not possible, the caretaker can operate easily with the G-pad or even with the app installed in the tablet. So this is the group of the students at that time who worked on this wheelchair, right? So now, before we proceed further, can anyone answer what all the sensors do you think that are used in this navigational platform? Actually, there are also actuators, right? Because the wheelchair has to move, but because I have not started the actuator yet, I am just restricting my question to the sensors that are used um, in this project.
So we have encoders.
What is that?
We have rotary encoders, sensors.
Okay, yeah, encoder is a sensor, right? But in this one, we are not using the rotary encoder because we are not keeping track of how much distance the wheelchair moved. Rotary encoders are normally used to keep track of how long the wheelchair or any robot traversed, right? So here we don't use the encoder. Actually, we are not using the encoder here. Right, so IR, I already mentioned the G-pad is made with IR sensor. So there should be IR sensor and a photodiode, right, to sense the light. So that are those two types of sensors, right? And there should also be an ultrasonic sensor to detect the obstacle, right? Because accidentally the wheelchair should not go and hit somebody or hit the wall, even if the user is somewhat not alert, right? The robot should be alert, so it should not go and hit. So we have used the ultrasonic sensors. Obviously, obstacles can be detected by simple IR sensor also, all right? But in this case, we are using the ultrasonic sensors, right? And if you take the tablet, there is a touch sensor, right? The screen is sensitive to touch, so there should have been a touch sensor used there. All right. So these are some of the sensors part of this navigational platform. All right. So we'll continue with the sensor topic. The most commonly used, or one of the most commonly used temperature sensors is the temperature sensor, exploiting the property of the diode characteristics, which can change with respect to the temperature. Right, so the diode characteristics are affected by the temperature. So that property of the diode is exploited in the transistor. Right, transistor, you know that it's similar to diode structure. So that property is exploited, and the amount of the current or the electrical energy is proportionally converted into a temperature value. And these are all very, very sturdy and a very precise one, because they don't have any moving part, right? It's just like a transistor, a BJT, right? Like the old way of measurement using mercury or bimetallic strips, right? So there you have some kind of a moving part in those kind of temperature sensors. And they are also very inexpensive, right? Maybe 20 rupees or 30 rupees, you get on LM35. And as I mentioned, this CO2 sensor, the carbon dioxide sensor, it is used as a signature of the human life, because in disaster hit areas, if some victim is stuck under a rubble and is struggling, right, the CO2 sensor can sense the presence of life. Right, well, research is still going on in this one. There are some commercially available CO2 sensors which sense to maybe few tens of centimeters, but research is still going on with detecting the human presence even as deep as 5 meters. Right. In fact, that is one of the sensor we are using in our one of the search and rescue robo. Right. So this, you can see a chamber or a tube. On one side you have an IR lamp, and on the other side you have a filter and a detector. So the infrared rays pass through this tube filled with a gas or air, and all the CO2 molecules absorb this IR rays at 4.2 microband. Right, so that is close to the microband absorption of CO2, which is 4.26. So if the IR rays are going to be absorbed by the CO2 molecules, then only the remaining CO2, the remaining IR rays only going to reach the detector. Right. So whatever that is reaching the detector, you can calibrate it and find out how much CO2 molecules were there in the tube. Right. So this is how it works. Right. And as I mentioned, the human body, right, radiates, or the carbon dioxide, if there is a huge amount of concentration of CO2 at some place, that means there might be a human presence in that place. Right. So next we go to the LDR, the light sensors. Right, light sensors in common detect the light and create an electrical signal. LDR is one of the most commonly used by the students for some of the robo projects. right? It's nothing but a kind of a photoresistor, right? And the electrical quantity is the resistance, right? It's the resistance is going to vary according to the light intensity. If there is very high light intensity, the resistance will be low. That means a huge amount of current can pass through. If there is no light, this acts as an open circuit because the resistance will be high, and huge resistance is similar to a open circuit. So the amount of current that flows will be very low. So this property can be used to measure the presence of light or the absence of the light, or how much light is present or absent. Now this TSOP, right, a thin small outline package IR sensor. All right, this IR sensor is also light dependent. All right, so normally what happens is that the for line detector, right, the commonly used the robotic projects, right, the detection of the line, they use this IR setup and a photodiode, right? So the IR rays go and hit the black line, and the reflected amount of light is captured by the photodiode, and accordingly an electrical signal is generated, and based on that, the robo can traverse as per the line on the ground. Right, but the problem with this kind of setup is that if the same setup is used under sunlight, because sunlight has a good amount of IR radiations, and that would affect the photodiode outcome. So you get a random output, you get a spurious output, not a predictable one. So your robo might behave in an unpredictable manner. It might not follow the line. Right. So that is where the TSOP came into picture. Right. This receiver. This TSOP is a receiver. Right. It is also based on a diode, pin diode. So in this diagram, you can see that the IR rays are modulated with respect to some pulse of known frequency. Usually it would be like around 34 to 38 kilohertz. Right. And this TSOP sensor or the receiver, you have to look at the data sheet for what frequency it is sensitive. Accordingly, you can modulate the IR signals. So what happens is that when the IR signal is modulated, hits the object and received, right? So the cover, right, of this package itself acts as a filter. It filters out the sunlight or the ambient light, which is due to your light source in your home, and it will allow only the modulated light. So by that way, you know that the transmitter or the IR is the only source that transmitted, and it's not mixed with sunlight or the ambient light. Right. So there is a pin diode, there is an amplifier, and there is a band pass filter. Right. So based on this output here, you can detect the intensity of the light, the presence of the line, your line following robo or hand gesture. In fact, we use this setup, a simple 5 IR TSOP setup only used to detect the hand gesture, right? So the entire platform would cost like maybe 1,000 rupees or so. That's it. Right. So now coming to the ultrasonic sensor, as I mentioned, right? So the sound here, acoustics is used. So you can see the setup here, one is the transmitter and another one is the receiver. Right, so the transmitter is going to transmit the acoustic signal, and it hits an object, and the receiver receives it back, and depending on the amount of the sound, right? So waves received, you can use a microcontroller and should be able to calibrate the distance of the object from your robot. Right. So now let us go to another video demo. Again, I'm thinking it's your audio is going to be a problem. So anyhow, I'll give a live commentary of what is going on. So I'll do a short introduction. Right. So this was an inspiration from a Google museum in Bay Area, California, because I happened to visit in 2013 this Google museum, and at that time, the first car, the Google car, was on display in the museum, right? So myself and one BTech student who had the opportunity to present a paper at a Global Humanitarian Technology Conference at San Jose, right? So we were discussing about the Google car, and then we came up with the idea if self-driving can be used for comfortness, why can't you be apply that to help some people, right? That is how we came up with the self-driving wheelchair, right? Unlike the other wheelchairs, powered wheelchairs, where you need to continuously navigate, even if it is joystick or your hand gesture, you need to keep moving your hand continuously, right? But here in this one, I'm not going to tell about the sensors because then right, the interest might be gone. So there are sensors used, right, create the map of the room, of the house, or of the hospital, or of the airport, or community center, or old age home. You can create the map of any facility. And once the map is created and fed into the system, the user can use the map and touch anywhere where the user wants to go. And that's it. The user can be reading newspaper or thinking something, but the wheelchair can automatically take the user to the destination. Right. So let us go to the video.
Life easier, but the technology can also be extended to wheelchairs.
So this is the self-driving wheelchair.
The interest came out after.
Sir, audio is there, sir?
Oh,
No.
audio is there? Oh, good.
To travel from one place to another in an airport, we realized that people with mobility issues face a lot of difficulties in their day-to-day travel, and most of the times have to depend on a second person. Our self-driving wheelchair, Self-E, can change the way the society looks into the wheelchairs. Self-E system has three phases. In the first phase, the wheelchair is driven through the environment where it has to operate and creates a map of the environment. A similar map is created in the Android application that we developed, where the user can point to the destination that he or she decides to travel to.
You can see the map is
Once
created.
the destination is pointed through the app, Self-E wheelchair plans the shortest path and moves the wheelchair towards the destination. The hardware equipment we use consists of a single laser scanner. This laser scanner can identify the environment and also moving objects like we do. The onboard software automatically reroutes the path while avoiding any sudden obstacles in its path. Our self-driving wheelchair, Selfie, is fully operated using any Android-enabled device like smartphone or a tablet. The users have three different modes to operate Selfie: manual, auto, and fixed modes. The manual mode has easy access to the wheelchair. with a simple direction interface where the user has to continuously navigate using the app. The fixed mode is used for navigating common places like shops in airports or rooms in hospitals where the destination is known in advance. In auto mode, the user can choose any destination on the provided map. The user has to just point to the desired location using the Android device and the wheelchair starts moving. Self-E can also navigate through tight spaces like passing through doors, corridors, and even getting into a lift. This autonomous technology can be used to deliver goods in industries, food in restaurants, people in airports, hospitals, and grocery shops, etc.
Yeah, so you can see that it has a good scope for transporting the COVID patients, right? Because the patient themselves can navigate, so thereby avoiding the direct contact with the wheelchair pushers or any caretaker. Right, apart from being used in general cases like elders or right, airport, you can see airport people need a lot of wheelchair, right? And the problem in the airport is that there will be a wheelchair pusher who would take from the entrance of the airport to the gate, right? For example, if these elders who are traveling in the wheelchair want to go for some food or a bathroom break and all, it will be very difficult because the wheelchair pusher may not help, right? So in such a scenario, if there is a self-driving wheelchair, right, people can be at their leisure, right? They can go to restaurant to eat, they can have a bathroom break, they can go for shopping even before reaching the gate, right? So now coming back to our topic, what are the sensors do you think that is used in this one?
So definitely a lidar has been used.
Yeah, very good. Yeah, a light detection sensor.
Light detection sensor, which
Yes.
actually maps the whole area,
Yeah.
and even the obstacles. Then
Yeah.
then we have encoders that were being used for the
Yeah,
motors.
yes, yeah, definitely. Because now this is a self-navigating one, so you need to know how much you travel, right? So that you can stop exactly where you want to stop, right? So there is an encoder being used.
Then
Right?
ultrasonic sensors have been used.
Yes, definitely. Because lidar is the 2D lidar, so it can detect only at one plane, right? If the obstacles are shorter, right, below the lidar placement, then the obstacle won't be detected. So you need ultrasonic sensor also, right? So this is the encoder, commonly used, an optical encoder being used, right? So you can see a disc, right, with a pattern wherever you see, and it's divided into like a wheel with the forks, right? So wherever you see a white, that means there is a hole through which the light can pass. Wherever you see black, that means the light will be blocked. So this is going to rotate. This is fixed on the actuator and this is going to rotate. Right. So depending on the light pattern that is received on the other end, you can keep track of how many rotations this disk has made, and accordingly how long the robo moved. Right. So each pattern corresponds to each pattern in the design corresponds to a digital pattern. So this is a 4-bit encoder, but encoder can be 10-bit or 12-bit or even higher, depending on the price you want to pay for. Right. So that is one of the critical thing in almost all auto navigation robots. Right. So now coming to the Kinect sensor. Right. So Some of you might have heard about that. It's very popular. I don't know, I'm not sure about now for gaming, right? So it gives a very good experience, a live experience, right? You don't need to actually hold on to something, right? A physical one, it can be a virtual one, right? And then the Kinect can do the job, right? But the Kinect is built with three sensors together. One is the camera or the light sensor, right? And then a depth sensor and also a microphone, right? So it is made up of three sensors. So camera can capture the light, RGB, right? And depending on that, you can actually recognize the face or the body. So that means this can be used for identifying a person, right? So that is kind of an eye, and the robo can know whether this person is a known person or an unknown person. The second sensor is the depth sensor. It uses a CMOS sensor and a IR projector, right? So by transmitting this near infrared light and based on the reflection from the objects, the depth of the object can be identified. So the Kinect can know how far an object is. Right? I'll show you a short video and you would definitely understand better how the Kinect sensor, the depth information is very critical for robots. And finally, the microphone, right? If you want a humanoid robo where you want to interact with the robo, you want to ask some questions and the robo replies back, or for a gaming reason where you can talk and control the game, right? So this microphone would be very useful. Right, but this Kinect is a complex system. It's not only sensors; it is also the electronics beyond the sensors. Everything put together in the Kinect. So here only sensor is shown, but you need or there is embedded software and an intelligent system inside the Kinect, right, to identify the object, for the face recognition, for the depth information, all these things. And this data, right, is integrated with the Kinect software. Right, it's a custom software. It is not an open software. So the sensor and the software are integrated together, and very advanced algorithms work on the data collected from these sensors for the facial recognition or depth identification or the sound recognition or the voice recognition. Right. So this is the LiDAR sensor, as I mentioned. Right. This is what we use in the self-driving wheelchair. Right. Particularly auto navigation, where you need to know in advance the environment, or even you can map the environment live while you are navigating. So LiDAR stands for light detection and ranging. Some people call it as light imaging and detection and ranging, and the original name was light and radar. Right. So this is also based on the reflected light. The LiDAR is going to, you can see this is a rotational one, right? It keeps rotating and sending this the laser light continuously. And there is another one here which receives the reflected light. So the light hits the objects as the LiDAR rotates, gets back into the LiDAR, and with the help of the time of the reception, all based on the same principle, right? When it is received, the LiDAR is able to map how far this object is. It will not know what the object is, right? It's not like Kinect, which has a camera. This has only laser scanner, so it can only map the depth. Right, so accordingly, a map of the room is created. And once the map is created, you have all the information you want about a room or a facility, and we can use that for the navigation. Right. So one more thing that somebody answered that you forgot to mention is the IMU sensor that also used along with the LiDAR information, right, to know whether the navigation is going in straight line or when to take a left turn, when to take a right turn. All these things depend on the IMU sensor, right? So the orientation is very important. The orientation information is also very critical. Not only the distance information, right? Because often it happens that the wheels are mechanical objects. So as such, there might be some misalignment between the two wheels, the rear wheels of the wheelchair or any robo. So that minute misalignment while traveling for long distances can cause a lot of error in reaching the destination. So you need to keep track of the orientation of the robo for which the IMU sensor is used. Right, but IMU is not a single sensor, it is like a system or a sensor unit. That's why it is called inertial measurement unit. It consists of accelerometer sensor, gyroscope, and also magnetometer. So it consists of three sensors. Right, so accelerometer used, right, to keep track of the axis, right, and then gyro is used, right. Do you remember, like, have you come across this accelerometer and gyro anywhere?
Yes, sir. Yes, sir.
Where?
Sir, I have actually used IMU as a whole unit, but I've seen the example of the wheelchair which I just shown there. It uses accelerometer and gyro to detect the position and the straightway motion of the chair.
Yeah. Yeah. Okay. So yeah, but right, one common item that all of us are using day to day life. Your mobile phone has the accelerometer and gyro.
Yes, sir.
Right. Because of the accelerometer only, right? If you rotate your phone, your view changes to horizontal, right? That is because of accelerometer. And you could see that some of the students, they play game with phone, right? They are able to rotate the phone, right, and control the gaming object. That is due to the gyroscope. I think that gives you a better idea about where accelerometer. So accelerometer is kind of a linear motion. Gyroscope is kind of a angular motion. Right. So this accelerometer, gyro, magnetometer is obviously Earth's magnetic field. It also gives whether it's like a magnetic compass, right? Orientation, north or south, right? Which direction you are going, you can keep track of it. Right. So that is so that is very important. We use the accelerometer and gyro, right, in order for the linear and the angular motion or velocities. So all these put together, and you need algorithm, right? Then only the self-navigation is possible, right? So obviously, camera is an image sensor. Many of you already know about so many things about camera, right? So there is a three-layer setup. The first one is the lens setup. The second one is the filter, right, and the third one is the photodiode, right. That's a common thing that is used in the camera. The optical light fall on the sensors, and the filter, right, red, green, and blue RGB filter, right, filters, and accordingly the photodiode detects the intensity, right, of the light that is falling on the sensor. And this photons on the photodiode going to create an electric signal. With this signal, you will be able to identify the digital data of the given image. And once you have a digital data, you can apply some algorithm and do whatever you want. Right. So that is about the image sensor. So now I'm going to show you one robot that we developed at the lab. Right. Let us see. Yeah. Is it audible?
No, sir.
You're not able to hear? I don't know why some works and some doesn't work.
Speech recognition
Can you
No,
hear?
no. Yes,
by
sir.
integrating the Android speech application to the IBM Watson chatbot, where the recognized data in the application is sent as a message data to the ROS master. IBM chatbot acts as an assistant for human-robot interaction. The mapping of the environment is done by gmapping package. This is the map of our HUT lab, which is divided into 4 different sections. Section 1, Section 2, Section 3, and Section 4. Navigation to the desired location is obtained by localizing through AMCL package and integrating it with move-based package. For object recognition with Kinect sensor, we are using an algorithm called YOLO, where the robot needs to be trained with different images of objects. The robot can recognize the trained objects and also gives the object midpoint coordinates with respect to the origin of Kinect sensor for pick and place purpose. In case of a person, the robot can estimate characteristics like gender and age. Currently, we are using the 6 degree of freedom Kinova arm for pick and place and for basic human-robot interaction. Here is an example of human-robot interaction where arm is used. We are currently developing a gripper to serve as an end effector for the arm to hold the objects.
Okay. So what sensors do you think are used in this one? Some of this we already saw, right? So the Kinect sensor, you could have seen at the top of the robo, right? Yeah, so that is the Kinect sensor here. There is also a mic attached to that for the voice recognition, right? So there is a image recognition, right? Object recognition. All the objects are, you can see laptop, bottle, right? Identified chair, right? So face recognition. So this manipulator, so the manipulator or the robotic arm also going to use sensors. Can anyone tell what are the sensors used in this manipulator? Okay, so that might be a difficult one. So let us see the sensors. As we look the sensors, we can get into the more details about the sensors used in the manipulator. Right. So next sensor is a load sensor. Right. If you want a immediate example, right, you would have seen electronic weighing machines in shops. Even in grocery shops nowadays, electronic weighing machines are used. Right. So you can see the weight in terms of the decimal number. Right. So the load cell or the sensor, right, that is being used in order to get the weight information. Right. So the forces such as tension, compression, pressure, or torque are converted into electrical signals. And these electrical signals can be calibrated, and the amount of weight or the force or tension, whatever you want to measure, that can be measured with that. There are several types of load cells: hydraulic, pneumatic, and strain gauge. Depending on the application, you can use you can choose one of these load cells. All right, a commonly used sensor, you might not have thought that it is a sensor, but a potentiometer is also a sensor. Right, so you already know it as it's a like a variable voltage, right, depending on the resistance, right? So depending on the varying voltage, you can measure the quantity you want to measure, commonly used for volume control, right? Volume control, you have the potentiometer, right? Or some needle control in your power supplies, or your some other measuring instrument. You can see even in joystick, the potentiometer is used. And one of the common application is the servo motors. To get feedback, they use the potentiometer, right, to get the feedback and keep the motor powered up. Right, so that is the actuator actually. Servo motor is actuator. So in that one, potentiometer is used. Right, now coming to the microphone, right, well, microphone converts sound into electrical energy. There are two types of microphones, dynamic one and the condenser one. Both uses kind of a diaphragm plate, right, where when the sound energy hits, it is going to generate some vibrations, and there is a voice coil which can convert these vibrations into electrical signal. So the dynamic microphone are commonly used in kind of open air theaters or some auditoriums, right, where huge sound is being dealt with. Whereas the condenser microphone is used in terms of voice processing, audio processing, where you need to even capture a minute sound in kind of a very controlled environment. You use the condenser sense microphone. Right, current sensor. Right, current sensor is also commonly used. The amount of power. These are all used in robots. Right, I can show one of the robots where we use. In fact, the manipulator I showed. Right, a current sensor can be used to find out how much current is drawn by the actuators used in the manipulator or the robotic arm. Because the robotic arm, it's like a human arm with joints. It can be 2-degree freedom, 3, 4, 5, 6, 7-degree freedom. So each degree of freedom will require an actuator, right? So you can keep track of the orientation and the motion of the manipulator, and also the health of the manipulator, depending on the amount of the current drawn by each of these actuators. If there is a situation where we sense that more current is drawn by a particular actuator than the threshold amount, then the microcontroller or the microprocessor can sense a danger and can switch off for the safety of the arm, right? So particularly these are all, the current sensor is used for as a safety measurement. Basically, any current carrying, it's a very basic principle, right, being used, right? It's not hi-fi one, right? Any current carrying conductor should produce a magnetic field, or any magnetic field that comes into contact with a coil should induce a electric energy, right? This is the principle that is being used in this current sensor. Then this Hall effect sensor, right? I don't know whether you have heard about this Hall effect sensor. It is for measuring the magnetic field, right? So this is particularly useful in some of the actuators, right? We are going to soon see, right? Other than a direct application of measuring the magnetic field, right? So this can also be used for using that magnetic field and controlling the motion of some of the actuators which requires precise rotation, right? So when magnetic field, when a magnetic is held near a plate, right, which is charged, you can see the charges deflect, right? So that is the property that is being exploited, and based on the amount of the charge deflected, the magnetic field amount or the magnetic flux can be measured. Right, so this is another sensor that is being used in the manipulators, advanced manipulators. You saw that the robotic arm that was used in that robo is a Kinova robotic arm. You can see this is the robotic arm you saw in the video, right? So that is a very, very advanced manipulator, a lightweight manipulator, which uses torque sensors. Right, the torque, what is the torque? So the torque is a rotational force, right? It's like you have a regular force, which is a directional force, right? Whereas the torque is a force in a rotational force. So depending on this torque sensor is built with the strain gauge. Right. So strain gauge is similar concept, similar to load cell. In fact, load cells are some of the load cells also use strain gauge. Right. So depending on the strain that is created because of the rotational force, right, this strain can be converted into electrical signal and processed and then calibrated to find out how much torque being used in the actuators, right? So that is about the torque sensor, and I think there are several other sensors, but I'm stopping here with the torque sensor, right? Then we are going to switch to the part 2 of the presentation or the lecture, which is going to be the actuators. So before we go that, is there any question in the sensors? Okay, either you under the dialogue we used to tell to the students when we ask question and they don't open the mouth, right? Either they understood everything or they did not understand anything if they don't ask questions, right? So I will assume the same. Either you understood everything or you did not. Yeah, well, you might not want to ask the question. That is also there. Some might feel shy to ask the questions, so that is fine. Right. So now we go to the part 2, the actuators. Right. So this is totally different from the sensors, right? Because sensor, as such, there is no mechanics involved. There is no moving part involved. You fix them somewhere, and they are going to be there. That's it. Right. But whereas actuator is the one which gives the motion to the robot. Right. So obviously, the moment we say actuator, the first thing that might come to your mind is the motors. Right. Normally, we don't use the term actuator. Even with the robots, we used to call motors are used here and there. But actuator is a proper term because motors mean there are. It's one kind of actuator. Right. So an actuator, the definition is actuator is a component, right, that is responsible for moving and controlling a system. Right. So you have a energy, right? You have to energize the actuator. So you supply the energy. There is a trigger signal or the input or the excitation, and the result is the motion or the force. So that means for an actuator, you need a control signal, a source of energy, right? So that is why we cannot call all motors as actuators, because you just energize a DC motor, it's going to start moving, right? But actuator, in definition, you must have a control signal. Even if you energize and if there is no control signal, there won't be any movement. The actuator would not move. Right. So there are commonly this 5 types of actuators. Hydraulic actuators, they use a liquid, right, a kind of a fluid in order for them to operate. Pneumatic, they use gas or air in order for them to make it work. And electric actuators is what most of the electronics and electrical engineers might have witnessed, because hydraulic and pneumatic are mostly used by mechanical engineers in some factories, some hi-fi stuff, but not in kind of robots that we build at the labs. Right, and there are mechanical actuators, purely mechanical in nature, right? The devices such as gears, pulleys, chain, these are all some of the mechanical actuators. And there are also electromechanical actuators, right? Like you have the electric motor, right? If you have a control knob with the electric motor, and you rotate the knob or the potentiometer, according to the motor speed can be increased. So those kind of actuators, you call them as electromechanical actuators. Right. So this is one interesting project. We have worked for this for several years. It was started in 2013. Right. We won several awards. Right. 2015, we won the best mechanical design award at a one moment robo glory competition in NTU Singapore. We won a second prize in an international conference on robotica, robots for humanitarian applications in 2016. Right, and we have published quite research articles, including journal papers. There was also a IEEE Spectrum magazine article on this. So of recent, we were one of the finalists in the Cisco Global Challenge for this particular project. Right, it's a very, very complex system. It's a challenging one, because most of the robots that are used, or you would have seen, right, they operate either in, they all operate in a known environment. Right, so you would have seen all the robots, right, operated in which the environment is predictable. Right, if you see a pick and place robo, right, it's operating from the ground, so there is no worry about the weight factor, the stability factor particularly. Whereas this robo for the coconut tree climber is a very, very challenging one, because it has to operate in an unknown environment, right? Because each coconut tree in the world is unique. So that means if we want a perfect robo, then you must have tested with all the coconut trees in the world, and which is impossible. Right. So, and also it is not operating on the ground. Right. It is going to operate, it has to climb the tree and operate somewhere at a certain height. And the tree structure is not a post or a pillar, which is of a predictable shape, right? Which is a known shape. Pillar is a known structure, whereas coconut tree, it's an unpredictable trunk of various shape, height, width. And in Kollam district, they have the cutting step in the coconut trees for the climbers to climb the tree. Right, and after reaching the top of the tree, the top structure is another challenge, because the coconut bunches of various sizes, various shapes, totally chaotic environment, right? And that is one of the recently, this is the 12th prototype that I'm going to show you, right? And we have not stopped the work. We are still continuing the work. Let us see what is there. There is an shortage. Can you hear the voice?
Yes, sir.
Okay. Anyhow, there is a caption. For example, in Kerala, there are 1 million coconut trees
50,000 trained climbers are required. In reality, there are only 7,000 trained climbers available according to the state's economics and statistical department data. The situation is same in all states of India and most of the Southeast Asian countries that produce coconut. Currently, there are different mechanical climbers available in the market in which the user has to go up with the machine for harvesting. We propose Amaran, coconut tree climber and harvester to solve this problem. Amaran consists of ground station, climber and harvester in which the ground station has a controlling device. The climber can be fastened to the tree with a spring mechanism. The climber is provided with a gate which can be removed while fastening the climber to the tree and then attached again. The circuit box attached to the gate consists of power management and control circuits required for Amaran. A Kinova 60-oil robotic arm with a customized electric cutter is used as the harvester. Using track motion, we are increasing the workspace of the harvester. Single D to 40 volt AC supply is required for the entire system.
Okay, so that is about the project, right? So some of the recognitions and award, we filed 3 patents, one US patent already approved for this, right? So now we will go to the some of the actuators, common actuators, DC motors. All the engineering faculty should know what the basic principle about the DC motor. You have a coil, and you know that a coil carrying current acts as generates a magnetic field, and obviously it can become an electromagnet, and that principle being exploited in almost all the actuators, right? So this is a simple DC motor which uses the brush, right, the carbon brush, to keep the contact, right, while rotating, right. The wires should not get twisted, so they use this carbon brush mechanism. Right. Now there is another version of DC motor, which is a DC geared motor, right, which is kind of, you have more control over that as compared to the DC motor, right. The DC geared motor produces a lot of torque, right. That means the load you can carry can be increased, right. And the DC motor, you don't have a control, right. A precise control is not possible. But whereas a geared DC motor, you can come up, you can bring some kind of precision into that, but not so much precise compared to the BLDC motors and the servo motors and all, right. Geared motors are not, DC motors in general are not so precise. And also the DC geared motors are costly because you have this gear setup, right? So you know that the torque, also one more compromise is that if you look at the speed and the torque, they are inversely proportional. If you want a high speed, then your torque will be less. If you want a high torque, your speed will be less, right? So that is something that is always binding these two. But still, geared motors are very much commonly used in robos. In fact, this is one of the robo we developed, the search and rescue robot. This is the 3rd version of the robo. I can show you the video that is there, which uses geared DC motors. Then the servo motor, right, for a precise control, servo mechanism is used. So there is a feedback with the servo motor, right? So you can have a very precision control, because if you want to accurately move only to in the length in terms of like millimeters, right, then you need a servo motor. For example, if you want to pick an object, pick and place robotic arm you are going to use, right? So there you can use you can build with a servo motor. But normally pick and place arm that the students build, they use the servo motors. But in reality, in the industry, they use BLDC motors because of a higher precision, because of they are able to afford to the cost, because the BLDC motors, they need a special controller which makes it very, very costly. Whereas the servo motors, you can use an ordinary microcontroller, even Arduino is enough to control. So the students find it easy, but for student projects it's okay. But there are very hi-fi servo motors which are used in industry. Right. In fact, we built you can see the robotic arm in this coconut tree climber. This is one of I told the one you saw in the video uses a Kinova manipulator or robotic arm. Right. That is the 12th version. So this is kind of 8th or 9th version. Till that time, we were using only servo motors. All the DOF, the degree of freedom, all the joints, we use only servo motors. But we had a lot of issues, as I mentioned, coconut cutting, right? We cut as bunches. You need very precision cutting. We had a lot of issues with the servo motor, right? Then we switched it to the Kinova arm, which used the BLDC motors. Right. So this is the servo mechanism. I mentioned something about the potentiometer being used. You can see that a part is being used. Right. The servo is made up of a simple DC motor, a high RPM DC motor, and a very, very compact gear mechanism. That is what it gives it gives its name servo motor. And you can ask the question, then how it is different from a DC geared motor, right? That is where the feedback comes into picture. In DC geared motor, you don't have the feedback through the potentiometer, right? So when you switch off, right, when you don't operate, right? Say you have powered the DC geared motor and you don't operate it, right? That is one scenario. And you powered up the servo motor and you did not operate it. The servo motor would be able to supply the same amount of current to the load attached to the servo hub, right? Whereas the load attached to the DC motor will not experience the same current if you just energize it and you are not operating the DC motor. So that is where the difference comes. So that is where servo is much useful in precision robotics. Right, so this is a search and rescue robo, right? A short video is there, you can see, right? So this is also one of and this is the third year we are into this project. We already built 3 versions, 3 groups of bachelor students worked on this. A 4th group is working on this. So this is the first version of the robot. This robo went to the Robo Cup Germany 2018. We were in Germany. We were the only team from India. So the second version, 2019. Actually, the first one was in 2017. This is 2018. Japan, World Robo Summit. We were there in Japan. Now we are testing at the lab. Second version. This is during the competition at Japan, Tokyo.
Slipper. വേറെ ആളെ ടീച്ചറാണ്.
So this is 2019 January. The third version, you can see there are only 2 clippers. So the operator won't be able to see the robot, right? There is a camera here in the arm, and through the camera, you can see the lidar sensor also used here, right? Through the camera, the operator has to see the environment and operate. Right here, there will be a cabinet for the operator to operate the robot. So this is the cabinet, right? So the operator can see only the video, what the robot sees. So this is a very, very complex system with several actuators and several sensors, multiple cameras, all should work in coordination, right? And also the operator cannot see the robot, right? So that is also another challenge. But that was a very, very good experience for us, all right? And then we are still working on so many things on that. Right. So the next one is the linear actuator. So you can see that in the first version of the robotic arm, we actually use the linear actuator to control the arm. Right. Usually, this kind of linear actuators you could have seen in the JCB, right? A very huge linear actuator being used to to excavate, right? Some things, right? So there is a motor or the DC motor, and there is a conversion mechanism. The rotational force will be converted into a linear force, which, right, a screw type mechanism you can see, right? So when this linear force can just tighten the screw or loosen the screw, and accordingly the shaft of the linear actuator moves. Right, so this is the another actuator, permanent magnet DC motor. That is what we used in all the wheelchair projects, right? All the navigational boards for transporting people. We use the permanent magnet DC motor. Usually in the DC motor, electromagnets are used, right? But here it is a PMDC because it can handle a very high power and it can be very compact. Because to carry people 80 kg average of human weight, you need a very high power motor. But if you go for a quarter HP or half HP motor that is used for pump set and all, the controlling part is very difficult and it occupies a huge space, right? And they are not battery operated, right? So those are the reasons this PMDC motor are compact, right? They are also controllable. You can have electric brakes with the PMDC motors. You can have a very high torque. It can handle very high load. So these are some of the advantages of the PMDC motors. So as I mentioned, BLDC motors are the commonly used motors for high precision manipulators. Right? Again, everything is you all game with your north pole, south pole, magnetic field, electric field, and how you set up or how you construct the motor. Right? That is what is makes whether you call BLDC or whatever motor. So obviously BL stands for brushless, because with the brushed DC motor, one thing is it's not so user friendly when it comes to control mechanism. Precision control not possible, and it has to be always energized. Right. So now this BLDC motor is brushless. Obviously, you can have some electronics to control the rotational force, right? And you can see the setup. There are multiple coils which generate a magnetic field in or a current in a certain way, right? You can see current A, current B, and current C being generated. And with the help of these currents, you can decode them and always know the position. They also offer a very high torque when coupled with the other drive mechanism or a gear mechanism. Very huge torque, right? In fact, we have successfully built one actuator at Hut Labs for one of our robotic applications, right? And we even have published a paper on that. A journal paper is still pending for the review. All right. So BLDC motors in common are used for the manipulators. They are really compact and use a very precision control. They are also very costly, right? Because of it comes with the electronics. And one more thing is it also comes with the Hall effect sensors. As I mentioned earlier during the discussing about the Hall effect sensor. So that is the one that is going to keep track of the rotation, right? So the encoding, it kinds of helps in the encoding, right? So you might not need a separate encoder, right? But normally my practical applications, our real-time applications, my experience is that even though you can use Hall effect sensor, we go for some other encoders in order to keep track of the position. All right, so that is about the BLDC motor. I think we have almost come to the end of the actuators. All right, maybe in few minutes we can close this. So this is a difference I already mentioned, all right, while discussing the slides, the DC and the BLDC. Obviously, DC is brushed DC motor, and BLDC is a brushless. So brushed DC motor, the carbon brushes wear and tear, right? And once they wear and tear, the outcome, right, the efficiency reduces. Whereas a robo, you are going to operate for several times and for a long time, right? And if your outcome is affected, efficiency is affected, the robo behavior is also going to be affected, which you don't want. So that is why for robotic applications, BLDC motors are preferred. Right. Obviously, if you have studied about the AC motor or DC motor, you could have studied about the AC motor. We, in fact, what we did was in our coconut tree climber, right? You saw the climbing part. The original one had a 10 RPM motor. It will take about 5 to 8 minutes to climb the coconut tree of 5 or 6 meters. Because 10 RPM is really slow, right? As I mentioned, we needed a very high torque actuators because the body will be very heavy, right? But it took a very long time to reach the coconut tree, right? What we did was we came up with a AC geared motor. We fabricated our own design, right? The advantage of AC is it has a very high speed, and the gear mechanism gave a very high torque. So that is why in the latest version in the video you saw, the robo is able to climb the entire 5 meter or 6 meter in 8 seconds or 10 seconds. It will just climb so fast, right? So that is about the AC motors, right? And one more thing is about the stepper motor, right? So you might have used some tiny stepper motor, particularly if you have observed 3D printers, right? You could have noticed 3 stepper motors are used for 3 directions, right? In fact, we built our own 3D printer, so that is why we know we use the BLDC motor. So what happens is instead of smooth rotation, right? It actually takes a step by, you can see, right? This structure is itself built like this, right? So the internal core is a multi-toothed magnetic rotor, and the external core, right? It's also kind of a multi-toothed one, right? So the north pole, south pole generated at each of the core and the rotor, right, keeps the motion of the motor, and then you can get up to a precision step of even 0.2 degrees, right? Step you can get. So you know exactly how much amount the extruder, you call the printer extruder, right? 3D printer has to move in order to print a 3D structure. So very precise one, right? It gives it's not so fast also compared to BLDC motor. BLDC motor can be really fast, right? And the precision is also very good, right? 0.2 or even 0.1, advanced one has 0.1 degree precision at all. So this setup is equivalent circuit is shown here, right? As I mentioned, the basic thing is only coil. You energize the coil, you create a structure whichever you want, and whichever motor you can create your own actuator, which you can call with some other name, right? Because the structure is such that basic principle is electromagnetic principle. Current carrying coil should produce a magnetic field and vice versa. Right. I think we have come to the end of the lecture. So if you have any questions, I would like to take now.
So thank you
Yeah.
very much for a very wonderful session, informative session. So there are a few questions.
Yeah.
We'll share the screen now.
Yes. So I will stop presenting. Yeah. Okay, the first question is, can you suggest best and reliable places to buy sensors and actuators? Actually, that is a very complex question because it took several years for us to even believe in something, because the trusted online source, as of now, I cannot say trusted, but because only they are available, right? robokits.co.in, you might already know, right? So they have good sensors and other stuff. But remember, whatever sensor and the actuator we buy in India, they are all cheaper ones, right? Because India is still, right, not investing so much money into robotics. India is still somewhere, right, compared to advanced, like I would say, maybe even 2 decades behind compared to the advanced robotics happening in Japan, Singapore, America, and Europe. That was my experience. Why? Because a student cannot afford to buy a 20,000 rupees sensor, right? Can you imagine? Because we still, right, and who should help? The industry or the government should help. But the industry university relationship in India is really bad. So whatever sensors you get and actuators you can buy, right, they are all like very low quality, low price sensors and actuators. If you want good actuator sensors, you can definitely buy in Germany, you can definitely buy in Japan, right? The European countries and even some companies in America, they also sell very good sensors and actuators. But can we afford to that? That is the question. Okay, the second question, which is the most used algorithms for the indoor navigation? Right, obviously SLAM, right, is the most used algorithm commonly used for indoor navigation. There is so much of research and nobody has come up with a better algorithm can SLAM other than the SLAM, even though there are many other techniques, right? How you get the information, right, that might vary, but the basic algorithm still remains the SLAM, right? Okay, which is the most algorithm for the indoor navigation? Okay, then there is another question, location tracking object, right? You could have seen, right, object identification, you need to go for machine learning algorithms. There are so many machine learning algorithms, neural networks you can apply, YOLO, object identification, speech recognition, some other algorithm. So you need to, you can, there are packages available. You can, if you know Python and machine language, machine learning, you can definitely do wonders. Third is, what is the most known used algorithm in indoor without implementing sensor in indoor infrastructure? Well, I don't know about that, right? Without a sensor, I don't know who wrote those questions. Can you elaborate? Because without a sensor, right, how can you navigate, auto navigate? Right, fourth question, has there been any robot developed in ATLAB to help blind? Yeah, actually, that was, right, it's like this, right? Student groups work on all these projects. So I am able to, one of the success of the ATLAB is that I'm able to find groups of the juniors to work with the project and continue for several years. But I'm not able to find motivated groups for all the projects. In fact, we had a very good working model for this virtually impaired, right? But that was stopped in 2016 or 17 because there was not further group to continue with that. May you suggest the best sensor and actuators can be used in the tendon-based robo, which is often, yeah, we have not worked on very small size, tiny robots, right? So I don't know about that. I cannot answer that question fine because I don't have any experience in that. How to design a snubber circuit when dealing with AC actuators? Right. Well, I was not. I not working on. Actually, implemented this circuit. Maybe one of our researchers might be able to answer that. Maybe I can. If you email me, I can see whether I can help you with that question. Which type of motors can be good for 60 to 80 kg of load? Yeah. So if it comes to a heavy load, right, you need high torque motors. That means you should go for geared DC motors or PMDC motors or servo motors. And you should always keep the cost in the mind, right? So geared DC motors are like moderate cost. PMDC motors are a little bit heavy cost, right? For 80 kg load, PMDC would be the one which can work better. But geared DC motors also can work, but the precision is again you need to look at. Right. So you can also go for servo motors. Right. But there is a company I forgot. We 100 kg load. We bought a motor that was around Torxis, 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 Torxis. Right. So that is a servo motor which can handle 100 kg load. right? But the problem is it's about $320. You need to pay $320 per that. So you have to keep up all this in mind while deciding on the motors for such load. Any other question? I think I answered all the sub questions.
Sir, no more questions, sir.
Okay.
Thank you very much for a very wonderful, very informative session.
Okay. Yeah. Thank you. Thank you so much for giving me this opportunity. I take this opportunity to thank Professor Deepa, Kochi Institute, and giving me this opportunity to share my experience with all of you motivated faculty. I hope that definitely, if it helps in some way, I'll be really happy. Thank you very much.
Thank
Yeah.
you so much, sir. It was a great pleasure listening to you.
Thank you, Professor Deepa. Thank you very much.
Sir, there is a request from the student, from the candidates. Can you please share your number and contact number and your ID?
Yeah, I will just type here, right, in the chat box, right?
Okay, sir.
Okay, so this is my number and this is my email ID. Yeah.
Thank you very much, sir.
Yeah, thank you very much. Thank you again for this opportunity. Have a wonderful day. Thank you very much.
Thank
Bye.
you, sir. With this, we are winding up today's STTP. The next session is scheduled at 10 a.m. tomorrow. Thank you for joining us today. The feedback for the first day is available in the chat box. Thank you.